Let's take a look at two derivative applications. First, distance and velocity, and second, a population model. For distance and velocity, we have a skateboarder who free fell 20 feet onto a ramp. The distance in feet traveled by the body falling and rest, given by this, approximately this function. Estimate the skateboarder's velocity at the moment he touched onto the ramp. So the first thing we think is let's do velocity, which we know is the first derivative of that distance function. But if we want to find out how fast the skateboarder was going when he actually hit the ground, we have to know at what time he hit the ground. So we've got to find t here using that idea of he fell 20 feet. So when did he hit the ground? He hit the ground 20 feet, and whatever t will give us that value. So let's go find that. So you put a 20 in for this distance, divide by 16, take the plus or minus square root of both sides. We only keep the positive one because we're talking time, not negative, so we're not in a time machine, so we're only going forward. So we get 2 root 5 over 4 seconds. Now that we have that, we know that that is the time at which he hits the ground. So now we need the velocity. We're going to put the 2 root 5 over 4 in here for t. So v of whatever our t is, 2 root 5 over 4, and then we get an approximation of 35.77. So that's the skateboarder's velocity on impact is 35.77 feet per second. Ouch. The next example is a population model. It's given by this function, and it's for deer in an area after t months. And we need to find the first derivative evaluated at 6 and at 30, and the second derivative evaluated at 6 and at 30, and then we want to interpret the meaning of those. Now 6 would be 6 months and 30 months. So pause the video, please go ahead and find the first and second derivatives of this function and then come back. When you take that first derivative, yes, you have to use the quotient rule. So it's derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all over the denominator squared. Go ahead and distribute and collect like terms, and when you do that, you get this function. We're going to go ahead and bring that exponent up to be a -2 so we can use the power rule to take the derivative. And when you do that, you bring the -2 down times the 150,000, keep what's inside, subtract 1 from the exponent, chain rule out the 4, then multiply 4 times -2 times this 150,000, and then go ahead and take this piece of the term down below in the fraction. So we then have the function, the first derivative, and the second derivative. So here are those 3 pieces of information. Now, what you need to do is evaluate the first derivative at 6 and 30 and the second derivative at 6 and 30. Go ahead and do that and come back and check your values. You should get approximately 15.3, 3.9, so interesting. After 6 months, first derivative. After 30 months, first derivative much smaller. Second derivative, 6, -1.2. At 30, -0.2. So check those values. Now we go back to the original question, and the original question is telling us this is a model of deer population after t months, and we have to interpret the meaning of these 4 numbers that we have, these 2 and these 2 numbers. So for the first set, at 6 months, the first derivative is positive and the second derivative is negative. So that means that the slope of the tangent line is positive, but that we are working with a curve that is concave down, which is saying that this is slowing down. So the rate of change of the first derivative is negative, so it is decelerating. The same is true here, that we have a positive first derivative smaller than this, so it is growing. The rate of change at 30 months is smaller than it is at 6 months, and it is decelerating at -0.2, and decelerating here, this -1.2. Now, the deceleration is slowing down as well. So the population is still growing, but it is growing at a slower and slower rate. Let's put that into words. So at 6 months, the deer, it should be the deer population, the deer population is increasing at a rate of 15.3 deer per month, but it is decreasing by 1.2. And at 30 months, the deer population is increasing at a rate of 3.9 deer per month, and that rate is decreasing by 0.2 per month. In the long run, remember we're asked a follow-up question. In the long term, the population is growing, but that growth rate is slowing down as time goes forward. And slowing down because we are already decelerating, but decelerating at an even faster rate. So it is slowing down and slowing down faster as time goes on. So that's it. Keep practicing those application problems.